converges regardless of whether it's contracting or expanding. So this part, and so if we have a fixed point that has both expanding and contracting directions, these definitions don't work because they'll give covariances with negative singular values and that doesn't mean anything. But this integral will work for regardless of the stability as long as you don't have marginal directions. And so we start and take this integral as the definition of what it means, how do we describe stationary covariance near a point with both expanding and contracting directions? Well, this integral will do the job for us because it works, reduces proper things in both the entirely expanding and entirely contracting directions. Okay?
Okay. Where do the transposes go?
Some of the transpose leaves everything block diagonal as well. So, now I'm going to multiply these through, and
The only term in question, really.
What?
The only term in question, whether it's block diagonal, is if you split up delta hat as two matrices, basically one with which is block diagonal by construction, and the other one with the other pieces.
Okay.
And the one with the other pieces is the
Right.
one in question.
Right. Okay. And I would like to show that the integral of the other pieces is 0, which will show that this whole thing is also block diagonal, which will give us this lovely picture of separating the expanding and contracting directions out. Matrix multiplication, lots of fun stuff. Okay. There's our 2x2 matrix, just direct matrix multiplication. And we also want to integrate this from 0 to 2 pi, d theta over 2 pi.
So mathematical.
Yeah. Okay, this is equivalent to integrating around the unit circle in the complex plane. Do you agree with that statement? So you're just integrating 0 to 2 pi d theta. You have all these e to the I thetas or e to the minus I thetas. Yes.
No.
Okay. Whatever, call it C.
But you have 2 terms. All right, go ahead. I'm sorry.
There's 4 terms.
4 terms.
You have, yeah, 4.
terms per diagonal.
Yeah.
Sorry, per block.
Right.
Right.
Yeah. And these are also all inverse, so they're not just, you can't just directly distribute them out. Still do good, this is now yes. Equal thing. Except now, instead of writing
You write it as Z now?
e to the I theta goes to S, and e to the minus I theta goes to S inverse.
So just a minute, please.
Sure.
You do, and you have labels.
Yeah. So if we look at the
E, C.
expanding term, then got its integral. Well, I'm just going to okay? We have that term. And that term is just, okay, so this term looks, I should call these S's. So I'm going to leave this in terms of d theta. Okay. So this term, still leaving it in terms of theta, this term looks exactly like one of these. Do you see how that works?
I have a question about the step before. I cannot justify the I on denominator.
Okay. Yeah, that's fine. It's just an integral around the.
Yeah,
Yeah.
it's a contour, it's okay.
Yeah, so it's just, right.
Yeah, right. Okay, then
That's just me writing down things when I'm only partially sure what contouring creation is.
you have the
Sure.
I once you get to the residue expression, but
Yeah, that's right.
after
Yeah.
integral formula value.
So this is the term that shouldn't vanish.
Right, this is the term up here. And this term shouldn't vanish, and it doesn't. It looks exactly like one of these integrals, right? So this term, call it QE, okay? Which is suggestively named the same as that QE. So this is entirely expanding, right? So this integral, we can solve it. We know that an entirely expanding integral of this form can be solved just by using this equation. Correct? So we're going to write down QE, and instead of trying to solve the integral, we're just going to write down QE, so delta E equals to lambda E QE lambda E transpose. Right? So this is how we did, that's how we, and this is a lot easier to solve. This is just a matrix equation. If it's diagonal, it's pretty much already solved. And so we can solve this for QE. Similarly, look at the contracting components. We're going to call this QC. And again, we have the same matrix here and here, so it looks just like this one, but with lambda c instead of m, and delta cc instead of full delta. And so this integral is equivalent to solving this equation. So this is QC, lambda c, QC, lambda c transpose, delta cc. These are our two separate equations that we're solving in the two separate subspaces. Now, EC. We hope this to be 0. That's this term. This is this contour integral. So we don't call this is S. Changed our names to S. Okay. Now this has different matrices here and here. So it's not just directly, it's not, you can't just say it looks like one of those. But we notice, and, okay. So where, but the question, next question, where is this singular? Right? So this is singular where, either where S is one of the eigenvalues of lambda C.
Where's it?
That's the transpose.
Okay.
Right.
Okay.
So S is one of the eigenvalues of lambda C transpose.
S minus 1?
This is just S, because it comes from there. Or S inverse is one of the eigenvalues of lambda E.
Should be the, if lambda E has an eigenvalue S, S minus 1S would give you 1,
okay.
and then you have a 0, and
Yeah.
that's what
Yeah.
it's single, right?
Right, okay, that's right. So
That's what I was
so
asking.
it's S inverse, so you have, if S
Is eigenvalue of lambda E, or S inverse is eigenvalue of lambda C transpose?
Yeah.
Okay.
Okay. But all the eigenvalues of lambda E have magnitude greater than 1. Correct?
Okay, yeah.
All the eigenvalues of lambda C transpose have magnitude less than 1.
Less than 1.
So all of these S's have magnitude greater than 1.
What?
Because S,
Yeah, yeah,
so
yeah,
S,
yeah.
magnitude of S is greater than 1, or magnitude of S inverse is greater than, so magnitude of S inverse is less than 1.
So you don't have a pole inside the unit circle.
So there's no poles inside the unit circle. So this integral is 0. Right? So you can just integrate around, contain the unit circle. Okay? Now for CE. This is now 1 minus. Also, delta doesn't have poles. It's just a matrix. Okay. So similarly,
You have same too.
right, so you have either S is an eigenvalue of lambda C, or S inverse is an eigenvalue of lambda E transpose. So at the same time, in the first case, your S is magnitude less than 1. In the second case, S inverse is magnitude greater than 1. So in this case, magnitude of S is less than 1, always. So we integrate, instead of integrating around the one way, we integrate around the other way, and then say, take some cutout to infinity somewhere. And so now you're containing the outside of the plane. So the inside of the plane So this one, this one you have no poles contained inside, so it's 0. This one you have no poles contained outside, right?
Mhm.
And so instead of thinking about integrating around
You-
the inside, you integrate basically around the outside.
Uh-huh.
And if you need to, you can go out to infinity and come back on the same line, so you really contain the entire
Uh-huh.
space.
Yeah.
So these two terms are both 0.
Can you draw the example contour for that?
Right.
From on one end you go to infinity and close the contour from infinity and go back like a branch cut.
Yeah, so this one, all our poles are up here.
Uh-huh. Yeah. That's
Right.
that's
This one, all our poles are around inside here. So instead of integrating around this, you say integrate around this, and then you go out to infinity and come back. And then out to infinity, sorry, I guess you go out to infinity, around the edge at infinity, and then you come back in.
so
And
this looks like cheating, right? So it's same integral. You have result of integral should be independent of contour you choose, shouldn't it? I mean,
well, it's the same.
why doesn't it work if it's 0
Yeah.
when you integrate around the unit circle?
These two are not the same. This one has lambda c here versus lambda
Yeah,
b.
no.
Yeah.
But I got that. But if integral vanishes,
Yes, it does.
then
Right. I just
why
want to
does it?
In order to show that the integral
Oh, okay.
vanishes, you need to show that the integral contains everything inside the integral has no poles, correct? But if you just look inside of this, there are poles. But outside of that, there aren't.
That, there are no.
Right. So you
Okay.
say that this integral is the same as going
Yeah,
to infinity,
got it.
going around infinity, coming back, and then
Yeah.
that,
Yeah.
because that's infinity, things are 0, and you just have the same line, so those two cancel each other out.
Mhm.
And so we know that this integral is 0 because there's no poles on the outside.
How do you also have to show that the integral itself vanishes? I mean, the integrand vanishes at infinity.
Right.
For this to work.
Right. So if we let s go to infinity,
I don't immediately see that.
okay.
I mean, it's just detail, but
Right.
if there's no simple answer,
You have,
I can live with that.
let's see, so you're saying if s goes to infinity, so absolute value of s goes to infinity, this term, those are the two s dependencies.
Yeah. And you and you should somehow show that the integrand should go like s to the -2.
Right,
So
so,
that it's
okay. I'm not sure about that.
I mean,
Just, yeah,
okay.
integrating around the outside.
Yeah, no, okay. The argument I just
So,
detail.
back here we said that we hoped that we could write our covariance in this separated form with QE00QC. And the Q, and over here what we've done is we've shown that if you separate this out into this block diagonal, this block form, the two off-diagonal blocks are 0. This is just QE, which is directly calculatable from that. This is just QC, which is directly calculatable from that. So, given the hyperbolic point, you take this covariance, you diagonalize the monodromy, sorry, the 1 times Jacobian M, do the right transforms on delta, solve the two independent problems, put them back together, and you have your covariance. Now, you can also, if you just want to think about the two individual distributions, you can only include the one, or you can only include the other. Right? So if you want to just think about what's the distribution on the expanding manifold.
You can just solve for the expanding.
Right.
Block.
So, this is also very easily generalizable to periodic points of maps, because okay. So the periodic points, we think back, this expression and the other one just came from evaluating how a covariance evolves either in the forward time sense or in the adjoint time sense, right? So we had Q n plus 1 equals to M Qn Mn. Right? So if you're just going to pick an arbitrary Gaussian, this is how it will evolve in time. Similarly, this is for forward, adjoint. We have something very similar. Let me make sure I write this down properly. Right. Yeah. Right. Because this time we're thinking of, let's show it this the other way around. Okay, those are our two main results from last time. So for fixed point, you're just sitting there, and you stay put, and so you say, what's the stationary covariance, so what comes back to itself after one time step. For a periodic point, you just say, well, what comes back to itself after you go around n times? Right? So a period, for here you go over here. Okay, so we have a periodic point with period, let's see, what did I call it there? Right. Period n. I used n up here, I used a over here. So now, I'm just changing the name of my label. Okay, so fixed point, for a fixed point you had to return after one time step. For a period n you had to return after n time steps. Right. Okay, so, right. Just say start out with 2. So I'm just doing 2 time steps forward. Okay. And For a stationary point, we'd set this one equal to that one. So for your stationary distribution, you'd set your come back after 2 times instead of just 1. For for 3, you do a very similar thing. So okay, so there's a couple things that it's important to notice. So first off, we're building up the entire Jacobian for the periodic point here, right? So those are just Jacobian and its transpose for the entire periodic point. Just the product of the one time step Jacobian that's along the way. The other thing is that you do not simply get the sum of the noise for each time step. Because the first noise keeps on getting deformed by the Jacobian of each subsequent time step. The noise is not just the noise, the sum of the noise. You have to transform each step. But, let's see, what do we... So we call this, right, so in general you have a bunch of terms like this. We call this M, the point P, period N. No, sorry. M for the periodic point P. It matters where we are, where we start at, right? So it will be different if you start at a different point around the periodic orbit. We're going to call this M a transpose, and this whole thing is our effective diffusion for the entire periodic orbit.
So, is there a reason for not writing down same stuff for the second or nth map?
For the fixed point?
Yeah.
Yeah, well...
You can...
Right, yeah, you can. And so you're just saying the second time step to this, right?
No, like in the very beginning, you have a map, right?
Right.
Of something.
Right,
So if you want to apply map twice, then...
Yeah. Yes, you could do that. The only cautious thing is you have to be careful about the noise.
So, yeah.
You have to make sure you not only add up noises from all the time steps, but also figure out how the noise itself evolves as well. So, yes.
That there's something that I don't understand about it, but that's...
Right, so the problem is, what's your effective, when you do this composition of F with itself, what's the effective noise?
Yeah.
So, the effective noise is not just the sum of it, like the noise builds on itself and the noise evolves with the dynamics as well.
So I'll ask the question differently. If M was one step Jacobian for the second order map.
Yes.
Okay. Then would the above equations be wrong for the periodic orbit?
Okay.
Yeah.
The M for the second order map is just this right here. MA, just the product of the two different ones, right?
Then it would be wrong.
Right, and so, well,
Okay.
right, well, if you replace, right, so if you take, at the second order map, you have a new Jacobian, right?
Yeah.
And the Jacobian, just by the chain rule, is the product of the two
Just call
Jacobians.
it period to order.
Yeah, period.
Yeah, period to order.
That's it.
Period to order. Yeah.
Order method.
Right. So your Jacobian, so you have new 2 time step Jacobian, and that's, by the chain rule, it's just the 2 individual time steps, right?
I guess.
There's a product of them, evaluate at the right position.
Uh-huh.
So that,
That's
Is this
the
term.
thing over that.
right.
Okay.
And then you have the question of what's the noise for the 2 time step map?
Yeah.
And that's where you have to be careful.
Okay, apparently there's...
So on this thing, this is just the Jacobian for the 3rd point, or the nth point, when you go around the circle. And when you go around this
Something, everything he's talking about is available in the blog, the Lippolis blog, so we can just give you links to the blog, you can check it out.
Okay.
You don't have to take notes, it's all there.
Yep.
He's written it up, we haven't published it, but we have.
Yeah. And then that you just have to worry about, because the noise doesn't just add directly. So it is the fixed point for the 2nd iterate map, but you have to make sure you get the noise right.
No, I mean, the second map is also a map.
Yes, it is.
Then where does the magic happen? I mean, at what stage? Because original map is a map, second map is another map, but the formula valid for the original map doesn't work for the second map.
Right, so we have this, and you're saying xn plus 2,
Yeah.
something like this.
Uh-huh.
Problem with this thing is we forgot the psi in the first term.
Okay.
So you have to have,
Yeah. No,
Yeah.
I wasn't actually exactly asking that, but yeah. So okay.
So when you take, if you just have the deterministic map,
Okay.
it's just a 2nd order map. And you can just take the derivatives of it, get the
Second
Jacobian.
iterate.
Yeah, 2nd iterate. Yeah.
Okay.
Take the derivatives of
Yeah.
it, and you get the same,
Uh-huh.
right, so without noise, you just have that, right? And you get the same form as this, where this is just the new Jacobian. Problem is, when you
Okay.
add in the noise, this noise is still being acted on by the map. So when you add in the noise, it's not just, you have to add in the proper extra amount.
Okay.
So, clarify things?
Yeah, I'm fine.
Okay. So right, so this is just QA plus N is right? So if we do this for n times around, these are just your Jacobians of the nth iterate map. And here's the total noise which has been acted on by the dynamics for each step. And this is in the forward time sense. We could also think about the adjoint time sense, which does the exact same thing. You can, if you just move delta to the other side, it looks identical, you just change the sign of delta. So that just makes all of these minuses.
It's
So,
QAN plus P, isn't it?
right. Let's make my notation consistent. Yeah. Right. So the adjoint does the same thing. You again have this total noise you have to sum over. The total noise which is expanded niche dynamics. And so here we get Okay? And then we set QA plus B equal to Q. And we have the exact same problem we had before. Just the different Jacobian matrix and a different amount of noise. So we can do whatever we did for the fixed point, do the exact same thing for the periodic point. And if it's entirely contracting, we use this equation. If it's entirely expanding, we use that equation. If it has some expanding, some contracting directions, we separate out the equations, solve them, separate out the components, solve them separately, and put them back together. Okay. So we've been doing this on the Lozi map. And
What map?
Lozi. Time? Okay.
Next lecture, how he applies it.
Yeah.